Mission control at T-minus 30 seconds and counting.
ECS reduced for launch.
Roger.
25.
Status check.
Go Atlas.
Go Centaur. Go AFSPC-5.
20.
Minus 20 seconds to launch TV4.
15.
This is Atlas mission control at T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. We have RD-180 ignition and liftoff. Liftoff of the United Launch Alliance AFSPC-5 payload with the Atlas V launch vehicle for the United States Air Force.
Vehicle disturbances are as expected.
You're now hearing the voice of Rob Gannon providing launch vehicle ascent data. Let's listen in for mission progress.
Everything is looking good. Passing 30 seconds into flight, everything looks good. Flight control is nice and smooth. Coming up on 50 seconds into the mission, everything looks good. Flight controls right down the middle, including normal disturbances for atmospheric flight. Everything is looking good. Operating parameters look good, vehicle disturbances look good. Open loop steering has been active for a while. Looking just fine. Coming up on Mach 1. And OTV is now supersonic. Passing through max Q. Vehicle disturbances continue to be as expected. We have throttled down to 95% of rated thrust right on time. Body rates are smoothing out. Engine operating parameters continue to look good. Continue to operate at 95% rated thrust. 20 seconds to enabling steering. Vehicles flying normally. Engines operating good. And we're proceeding right down the center of the range track, right as expected. Coming up on steering enabled. And we've enabled steering. Vehicles maneuvering. We are now 25 miles in altitude, 15 miles downrange, traveling at 3,000 miles per hour. Parameters continue to look good. We're now throttling the engine to maintain a constant 2.5 Gs for payload fairing jettison, and we fired the power valve, activating the reaction control system on the second stage. Everything's looking good. Continuing to maintain 2.5 Gs in preparation for fairing jettison. Engine continues to throttle as expected to maintain 2.5 Gs. Parameters looking good. Coming up on payload fairing jettison. Everything looking good. Getting ready for fairing. We're at fairing set. And CFR deck has jettisoned as well. Engine is throttling back up to 80% rated thrust, right as expected. Vehicle's operating normally. We've started boost phase chill down. We're now entering our constant 4.6 G acceleration phase in preparation for shutdown. Everything looking good. Coming up on shutdown. Boost phase chill has terminated as expected. We have cutoff. Booster engine cutoff coming up on staging. And we have stage separation. Everything looking good. We have pre-start on LOX and fuel. Ignition, full thrust. The RL-10 is up and running normally. Good start signature. Operating parameters for the RL-10 look good. The vehicle continues to fly right down the center of the range track.
This is Atlas Mission Control at T plus 5 minutes and 1 second into the flight. We've just heard Rob Gannon report the successful execution of events comprising the early portion of today's mission, and all systems continue to operate nominally. With the mission underway, let's take a look at video highlighting the capability of the X-37B orbital test vehicle. We have ignition.
This is the X-37B. The Boeing-built X-37B Orbital Test Vehicle, or OTV, continues to make history as the first unmanned vehicle to return from space and land on its own. The X-37B provides a highly flexible demonstration testbed platform for a variety of orbital experimental missions.
The X-37B testbed platform is unique because we can tailor our missions to specific user needs and return experiments back for post-flight inspection.
Building on multiple missions, the OTV has proven a reliable fault-tolerant architecture through launch, flight, recovery, and refurbishment cycles. OTV Mission 1 validated the concept with 224 days on orbit. Mission 2 pushed the envelope to 469 days. And Mission 3 not only shattered the record with 674 days on orbit, but also demonstrated the ability to reuse an X-37B flight vehicle.
These missions have proven the reliability and flexibility of the system to support a variety of experiments.
The X-37B offers a consistent and repeatable test platform in the space and hypersonic entry environments. As a reusable system, hosted experiments can be inspected, modified, and flown again at dramatically reduced cost.
Leveraging the existing X-37B infrastructure and reusing the platform allows users to focus their investment on the experiment and developing new technologies.
Responsive to rapid integration, the X-37B can fly and test multiple new technologies, reduce technical risk early in product design, and validate system performance. Integrated experiments leverage onboard power, telemetry, orbital maneuvering, thermal and attitude control to enhance test parameters.
The partnership between Boeing, Space Florida, NASA, and the Air Force is establishing the capability for the X-37B to launch, land, and process for reflight at Cape Canaveral. This will further reduce cycle time, providing even more responsive access to space.
Ready to fly to base technologies, today's X-37B enables affordable access to orbit.
The reliability, reusability, and responsiveness of the X-37B will fundamentally change how we perform future space missions.
As I mentioned earlier, in addition to OTV-4, today's flight includes 10 CubeSats. One of those CubeSats is LightSail, developed by the Planetary Society. And I'm pleased to welcome Planetary Society CEO and science guy, Bill Nye.
Thank you, Steve. It's great to be here.
Well, Bill, thanks so much for joining me. It's a thrill and an honor to meet you.
We're in the control center, for crying out loud. How cool is this?
Doesn't get much better.
Do we call this mission control?
Absolutely.
It's cool.
Okay. The Planetary Society has a CubeSat named LightSail on today's mission. Now, would you give us a quick overview of the project?
Yeah, so this may surprise you, us, anybody, but light has momentum, even though it has no mass. So if you can get, I mean, it's even when we're sitting here and light's hitting us, impinging upon us, we are getting a tiny, tiny, tiny push from the photons. Well, if you're out in space where there's nothing to stop you, and you have a big enough object, big enough sail in this case, and a low enough mass spacecraft, it gets pushed. And so Carl Sagan, my some other technical problems. But the guys involved were Carl Sagan, Lou Friedman, my predecessor at the Planetary Society, and Bruce Murray, who was the head of the Jet Propulsion Lab at that time. And they wanted to have a solar sail to prove that the technology would work. It's one thing to sit in physics class and show that this should be possible, but it's another to really do it. As Tex Johnston, the test pilot on the Boeing 707, said, "One test is worth 1,000 expert opinions." So those three guys started the Planetary Society in 1980. I joined. I've been a member ever since. And then I joined the board in 1997, and everybody has been talking about a solar sail since then. I mean, since 1976, people have talked about solar sails. And so the Planetary Society got some funders, especially Ann Druyan from the Carl Sagan's estate, Ann Druyan's Carl Sagan's widow, from his estate, and we tried to fly in 2005, Cosmos 1, but it ended up in the drink. It's in the Barents Sea, somewhere in the Arctic Ocean. And so 10 more years have gone by, and we've rekindled the idea and embraced the standard called CubeSat, which is just 10 centimeters by 10 centimeters by 10. But ours is a 3-unit CubeSat, so it's 10 by 10 by 30 centimeters, smaller than a shoebox, everybody. And then the sail that will come out of it is this super shiny mylar. And another just sort of surprising thing until you think about it, if it's shiny, specular, like a mirror, the photon bounces off going this way and goes back that way, so you get twice as much momentum as if it were black, fully absorbent, black body, what have you. So it's just like, you're kidding. Like, that's going to work. So this, out of this little box, these really cool, really wonderful material. It's high cobalt steel, which was manufactured at the Air Force Research Lab at Kirtland Air Force Base in Albuquerque, New Mexico. These things come out 4.7 meters, and the sail then is 32 square meters. I mean, it's an enormous thing with this little, less than 10 kilo CubeSat. And so we're very hopeful that the thing will deploy properly, sunlight will hit it, and get a push. Now, this mission, and I love you all, of course, at Atlas V land, but it's not going especially high. So we're going to get dragged down by the atmosphere pretty quickly. But this is a test flight. There's two things that we really want to verify. Telemetry with the ground, which includes pictures from our cameras. We have really elegant cameras built by Aerospace Corporation. And we want to see the sails deploy, because if you're scoring along with us, NASA launched a spacecraft called NanoSail D. And for those of you who are normal or whatever, D, capital D in aerodynamics means drag. So this thing was designed to be dragged down. And the sails didn't deploy for about 6 weeks. And no one's really sure why that was. It's just stuck, mechanically stuck probably. And then every time you go around the Earth, you get hot and cold, and it shook loose. But we are pretty confident we have solved that deployment problem. There is no thermal vacuum chamber on Earth big enough to have all 4 sails deploy at once from our little spacecraft. So we're going to fly it in space and see if it really works, and we're pretty confident. And just remind everybody, this was built by our members. 40,000 plus people around the world who just thought this was an intriguing and wonderful thing to experiment with. And it's a technology that we strongly believe will enable all kinds of missions to the moon, to asteroids, to Mars, and the other just really sort of practical application of a solar sail is to get in an orbit closer to the sun than the Earth, and then instead of getting pulled in, because when you're closer to the sun you'd have to go faster, let the solar sail keep your position, so-called station keeping with the Earth. And that could have all kinds of advantages for monitoring solar weather and for looking for Earth orbit crossing asteroids. What you really want to do is look for those in the infrared spectrum, because in the visible, it's, as we say, it's like looking for charcoal in the dark. It's really hard to see. But with the solar sail, we strongly believe that all sorts of universities, institutions, and especially the Air Force is quite interested in this technology, and we have worked real hard to keep the cost very low and the the compactness of it, keep the space very small. The space, that's a pun. The volume it takes up very small. So it's very exciting to be on the Atlas V.
Okay, well, ULA has launched 5 CubeSat missions already. I'd like to know how important are these missions in terms of the experience they provide to the students, the research groups, as well as the science and technology advancements we gain from these really low-cost investments.
Yeah, so the CubeSat is very small for starters, but the other thing is it's standardized. So you can go online and buy solar panels that are robust enough to take the hard vacuum of space in the sun, on the sun side and the night side, over and over. Without the thermal problems you would have with a homeowner's solar panel. And you can get electronics, you can get software, you can get software modules, and these things are becoming standardized, which has enabled universities. But the U.S. Air Force is quite interested in them, and Jet Propulsion Lab and Applied Physics Lab have both expressed strong interest. We have a lot of members there. Strong interest in the success of this particular style of CubeSat because it has its own propulsion. When you're using solar energy, it's there all the time. And so although it's a very small thrust, it's continuous rather. And so you can go hypothetically as far as you want in space.
Well, given the Planetary Society's unique mission, I imagine the CubeSats are an important part of its puzzle.
Oh, yeah. So one of the problems we had with this Cosmos 1 Russian-built solar sail in 2005 was every part of it was custom-made, every part of it. But now it's launching from a standard P-pod, which is another tortured acronym. I think it has the word Pico satellites in there.
Yeah.
And so it's a jack-in-the-box that is a standard size, a standard thrust spring with a standard release mechanism, a burn wire, that's all figured out. So that part of the mission that's been solved. And you guys at ULA have solved it, would you say 5 times?
5
times.
times.
Yeah, so it's very high reliability. And I'll tell you, our members, we launched on a Russian rocket, 2005, and it ended up in the ocean. They would not, they're very happy to be aboard a U.S.-built, high-reliability, big-time rocket. So thank you, guys.
Well, thanks a lot. Well, I'd like to shift gears just a little bit, and I think you'll find this interesting. It seems we have something in common. Each time I host...
Even more?
Even more. And each time I launch I'm in an Atlas countdown and host this broadcast, we get questions from our viewers about my tie.
Your tie. Oh, yes.
It
has pictures of a rocket.
That's right.
It has a space shuttle.
That's right. And I know that you're known for your ties as well.
Yes. But you choose not to wear bow ties.
That's right.
Takes all kinds, Steve. I don't get it.
And there's a reason for it. This tie has a history. And the history of this tie is, in 1998, when I was working on the other side, I was one of the folks that...
when you say the other side,
the other
side of the glass.
No, the other side of the river here, the Banana River, which is separates us from the Merritt Island, which separates from the Indian River to the mainland. The NASA missions are launched on the other side. We're actually on Cape Canaveral.
Yeah,
right
so we're
here.
on an Air Force base.
We're on an Air
working
Force
in
base.
the civilian zone.
That's correct.
Yeah.
And I got to work on the STS-95 mission. I got this tie when I was actually called upon to set some of the switches up on Discovery for John Glenn's flight.
So you threw some switches.